Is Physics 2, Lab 4, which in this case we were doing the magnetic dipole of a bar magnet. So a brief introduction. So the purpose of this lab was to measure the magnetic field due to a small bar magnet a different distance away from the magnetometer, which was located inside of a phone. Then additionally, these measurements were then used to calculate the magnetic moment, and then we use this magnetic moment to model to create a glow script model, and then we compared the simulated value to the experimental findings. So the calculated dipole moment was 1.855 ampere per square meter. The magnitude of experimental the magnetic field experimentally was found to be 77.79 microteslas, and magnitude of the simulated off-axis magnetic field was found to be 34.57 microteslas, which interestingly is about half. So a few key physics ideas that are important for an understanding of this lab is just the magnetic field of a dipole, which is equal to B times the K value, K magnetic value times 2 mu, which is the mu is equal to the moment over distance, or r, the r vector, magnitude of the r vector cubed. And also the distance dependence formula is important to remember, in that the magnetic field is proportional to 1 over r to the third. So here's the data from the lab. It was collected in the Excel sheet, and this was found by using a magnometer of the phone and setting it on the north to south axis, and then placing the magnet at different distances to achieve a specific magnetic field. And then the distance was recorded at which that magnetic field was reached. As can be seen here, the ln of the distance and the ln of the field, or the strength of the field at these points, was taken and plotted together. This can be seen to have a negative slope, showing that as distance away from the source increases, the magnetic field decreases in this case. Also, the off-axis field was calculated, and this was found to be 7.787, which was shown earlier. And this was simply taken by moving the phone, or moving the magnet off axis, and at about 45 degrees. So here are the calculations. This is how we found mu. Fairly simple, and using the y-intercept found in here, which I think is 14.807, then plug that in and find mu. So a few observations. So when the magnetometer is far from the magnet, it measures a near zero magnetic field in the x direction. This was found to be true. And additionally, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So again, this can be shown with this slope, and it should approach near zero as you move it even farther away. Here's the code. This first one is just initializing several variables, and our mu mag that was experimentally found is plugged into here, as well as setting the observation locations and the distance and the scaling. This is now creating vector arrows for the force at all the different locations, both perpendicular and on axis. And now here we simply find the dperp and also find the off axis, and also plot the off axis field, the off axis field. And here's the code results. As you can see, you have the force moving parallel in orange, perpendicular in cyan, and magenta is the off axis field. So a few assumptions is we would assume the bar magnet behaves as an ideal dipole and treated it as such. We also assume that there's no interference from any other magnetic fields aside from the Earth. So we assume that the magnet of the person next to me had no effect on mine. A few possible errors is that I could have had inconsistent placement of the phone, error in calculation, or also just like shaky, and it's hard to read the magnetometer exactly because your hand's shaky and it's hard to get a constant number. So what if you hadn't orientated your phone hadn't oriented the experiment to compensate for magnetic north and had instead, laid out the meter stick at some random angle. So the Earth's field then would have interfered with the X component, making it very difficult to glean the actual effect of the bar on the magnetic field, because you'd have this magnetic field of the Earth kind of making things wobble back and forth. You'd have to do all this complex math, and it also had to take some from the Y and some of the X. It just make things entirely more difficult. It was not impossible, but incredibly a lot more difficult. And also, what if you were to stick two identical magnets together end to end and run the experiment again? Like, well, how would it differ? You'd expect a stronger magnetic field. It's crazy. You'd end up producing a higher dipole moment. However, the direction would remain constant. Thank you. I appreciate it. Thank you.